this whole academic year, actually. And very pleased to welcome Professor Krishna Garikipati from the University of Michigan. Krishna is a professor of mechanical engineering and mathematics at Michigan in Ann Arbor. And he's been at Michigan for more than 20 years after obtaining his PhD at Stanford. And he currently directs the Michigan Institute for Computational Discovery and Engineering, which is, a broad institute, kind of the computational science and engineering plus center in that university. And his research is in computational science with applications drawn from materials, biophysics, mechanics, and biology. And a lot of his recent work is focused on data-driven approaches to computational science. And Krishna has won a whole range of awards. I won't give you the whole list, but they include the DOE Early Career Award, the Presidential Early Career Award for Scientists and Engineers, and a Humboldt Research Fellowship, and many other things. So really pleased that Krishna could visit us virtually today, and I'm looking forward to an exciting talk. So please take it away.
Thanks very much, Yusuf and Nicola, and also Kate and everybody for joining. Obviously, very pleased to give this seminar. It's always very special to converse with people at MIT, work with people at MIT, and even though this is remote, I'll try to do the best here. So you can see the title of the talk. So this is work that we've been doing for about the past year and a half or so, and we're trying here to contribute to this growing effort in applying essentially machine learning methods to PDEs. Okay? And straight away, let me acknowledge my postdoc, Xiaoshuan Zhang, who's developed many of the ideas that have gone into this, and definitely, as you may imagine, all of the implementation and computation. Okay, so, all right. So let's dive right in. So we've been applying data-driven methods in machine learning to a range of problems over the past 4 or 5 years, and the graphic on the right shows some of our efforts here. So we've been using machine learning methods to do scale bridging from quantum through epistemic through continuum microscale. And we're trying to be very rigorous about this. Also at the continuum microscale and at the macro scale, we are developing these system identification methods, essentially system inference, right? To given data, can you tell me what equations govern these data? And we also cast that as physics discovery in some cases. Also at those scales, especially the continuum microscale to the macro scale, we're using machine learning methods for homogenization. And finally, we're also doing some graph theoretic methods to develop reduced order models that function more at the sort of engineering system scale. PDE solvers, if we can get them to work nicely, could really encompass all of this. That's where we're going, and I certainly won't claim that we're there. We're just taking our first steps in this direction. So why would you care to do this? Why would you care to bring machine learning to solve PDEs when we've had discretization methods for a long time and they work well? The goal here would be high throughput solutions of PDEs, right? If you want to solve PDEs and at numbers of PDEs rapidly, and where would you want to do this? If you were interested in optimization, inverse modeling, this idea of multi-fidelity modeling, which requires you to go across many different types of problem descriptions, design, and so forth, right? So these are the kinds of applications. I'm not going to get into those. That's just what motivates it. I'll try to focus on the methods that we have here. Of course, we're not the only ones to be thinking about this. When we look at this problem, we broadly classify the approaches as consisting of surrogate models first, where you are using machine learning methods to learn solutions, but often these are in the forms of in terms of quantities of interest, right? You may not be solving like full field solutions. They tend to require large amounts of training data. UQ can be done, certainty quantification, of course, can be built in. There's lots of related work. This is a very, very small sampling of some of the works that we've referred to, and doubtless there are others, and there will be more in time. When it comes to PDE solvers, there's a slightly different approach that we consider to be defining this class of methods, this class of approaches. So what you're trying to do is you construct a loss in machine learning methods, where you embed the PDE and its boundary conditions in some way, right, into the loss. The claim here is some people, there are quarters that will claim that this is machine learning with no data, We wouldn't go quite that far, but we do acknowledge that there's a difference in the way we look at data here, right? With little or no pre-labeled data, and you'll see what I mean by that, at least what I mean by that. Others may not agree with that, but you'll see what we mean. Anyway, UQ can be done. Also, a lot of work here. Again, we've listed some of them. The lines that we followed, and like I said before, I have no doubt that there are very significant omissions here, and we apologize up front. We'll seek to learn more about them. Okay. All right, the goals of our work. We want to have we're doing neural networks here, so we're looking at a neural network-based PDE solver without, again, emphasize traditional labels, right? We're not using traditional labels. We want to solve multiple boundary value problems. Sorry, I didn't introduce that notation. BVP is for boundary value problems. So we want to solve multiple boundary value problems with different boundary conditions, different problem domains, right? So as indicated by these polygons here, and we stick with polygons here, again, understanding that a lot of foundational mathematical work for the Poisson equation or the Laplace equation has often been started out on polygonal domains. And of course, we know that they have good, one can approximate many geometries as high dimensional polyhedra, high order polyhedra, and so forth. Okay. So we are seeking to solve these PDEs on different polygonal domains, and I've kind of color-coded boundary conditions here. Red and green could be Dirichlet boundary conditions, blue could be non-zero Neumann conditions, and no color of just black could be zero Neumann conditions. But anyway, the goal is we want to be able to solve PDEs, these boundary value problems, with different boundary conditions on different problem domains, right? But of course, we're going to have them all. We're interested in solving problems governed by the same PDE or physics. And what this means is that we're really seeking to have the method understand the PDE and not be just blinded by a particular set of boundary conditions or domains, right? And obviously, the progress needs to be made in that direction. But that's where we want to go. Having done that, we want to be able to predict for unseen boundary conditions and domains. And like I said, we want to do UQ, both epistemic and aleatoric uncertainty. Okay, very quickly, this is how I'm going to approach it. I've gone through a very quick motivation. I'll get to the problem definition. Yeah. All right, so we're going to focus here on a few specific elliptic PDEs, classical ones almost, right? So we're going to look at steady state diffusion. We have the flux H driven as shown here. C would be a concentration, D would be a diffusivity, and so on. Now, when it comes to solving PDEs, we admit to a bias towards the weak form. Our original training was in finite element methods, so we adopt the weak form. We adopt the weak form for a number of different reasons, depending upon the kind of problem we're looking at and what we're trying to do. For this work, our preference for the weak form is because it quite very conveniently encodes boundary conditions, right? So they're all in there in the weak form in some way. I mentioned finite element methods, and in that context, you go to a discretized residual, and I'm sure pretty much everybody here may be familiar with that. I'm not going to describe finite element methods or anything like that, but just mention that you have a residual, and the big A is the assembly operator, B is the discrete gradient operator, and so on. And as I mentioned, you code in boundary conditions, right? Neumann boundary conditions are right here. We also are interested in linearized elasticity. The standard constitutive relation with Lamé constants. The discretized residual looks pretty similar, with the stress making its appearance and the traction as Neumann boundary conditions. We also want to do nonlinear elasticity. I've written out the kinematics in the first line, F being the deformation gradient and so on. We work in that case with a compressible neo-Hookean strain energy function written here. Probably familiar to many people here. The first Euler-Kirchhoff stress is obtained from it. It's that relation. We plug it into the weak form, turn the crank, you get a residual. This is it. The Euler-Kirchhoff stress is in here. The traction boundary condition. Okay, so these are the three boundary value, the three PDEs we're going to look at, and the residual will play an important role in what I will describe. Okay, so let's move on. Neural network architecture. Sorry, excuse me. Okay, so this is the architecture that we work with. I mean, broadly defined, right? Of course, we learned this architecture gets developed along the way. As you can see, it is, it really, okay, so we really use this idea that we want to solve field problems. And so we really look at, think of every boundary value problem as having some field on it. So we think about images, right? And so we will have inputs, which will have multiple channels. The channels will not involve actual labeled images, right? Instead, what they will have are the boundary conditions, right? So we imagine that you're passing a domain, a square domain here. The red and green could encode Dirichlet boundary conditions. The blue could encode non-zero Neumann conditions, right? So that's the input. It turns out that because we want the system to focus on the boundary conditions, we need to kind of blind it to what may be going on inside. So on the interior of the domain, on the channel that comes with the Dirichlet boundary conditions, we also fill the interior of that domain with random numbers, right? We want the network to not learn anything from the inside, but just learn from the boundaries, okay? Just learn the boundaries, in fact, the boundary conditions. As you can see, we have the CNN-based encoder-decoder architecture here across all our networks. The usual kind of technology, multiple filters with kernels, stride rates, zero padding, and so on. We have max pooling, usual things, right? So you add more filters. You come all the way down to the latent space where we have fully connected layers, and then the decoder again expands out everything, right? So you have upsampling. At the end of all this, the neural network will have learned or will have learned some solution. Again, it's a field, okay? Now, how does it learn this? Because it will learn a solution and learn that it belongs to the PDE, that it solves a PDE, because after that, we impose a PDE loss layer. And this is where the interesting things really happen. So there are three channels here, broadly speaking. One comes from this solution, right? And then the other two channels are what I mentioned back here, right? It's the same as the boundary conditions, right? So feeding all of this together. We take all of that, assemble residuals. There's the residual which comes from the bulk of the domain. There are the contributions from the Neumann conditions. You pack it all together. You get rid of Dirichlet conditions. That's just the way you would do it in a weak form based method, right? Like finite elements. But all of this is done within this loss layer. And that's it. So once you have that, maybe you do batch-wise. You treat the data batch-wise. You define the loss per batch as shown here, where if you're doing a deterministic network, I'll talk about Bayesian networks next, but if you're doing a deterministic network, the loss is just defined as the square of the residual, okay? Over all the samples for each batch R. So that's the architecture. Broadly speaking, that's the approach we follow, right? The detailed architectures would be different. When it comes to Bayesian neural networks, the classical Bayesian approach, of course, we start out with Bayes' theorem. We have some prior here theta now are the parameters which would correspond to the weights of our networks. We have a likelihood, which I'll say more about. We have the evidence, which is usually the problematic part, and I'll tell you how we treat it. And then, of course, you have the predictive posterior. The exact posterior, and then is replaced with the more tractable surrogate distributions. And so and that is obtained by minimizing the KL divergence, right? The Kullback-Leibler divergence, all very standard. That then brings the evidence into it, which is the problem usually. So we go to elbow, right? Which is the evidence lower bound. It's equivalent to the KL divergence up to an additive constant, and that additive constant is the evidence, right? So you can pull that out. Standard definitions for it. So finally, when we come to the Bayesian neural network, BNN here, the loss that we have involves the KL divergence and the log likelihood, right? That's what, and together, so this gives us the elbow.
Excuse me, I have a super quick question.
Yes, please.
P of D in the denominator, I mean, it doesn't have the parameters. So why do we even care about it?
No, that's exactly right. So that's what is done. So it gets dropped out when we go to elbow. So
okay. Yeah.
So exactly. So you're optimizing it. Your minimizer, if you find it, is the same, right? So you just put it out.
Yeah.
Exactly. That's what we're doing. That's why we go to elbow, actually. Thanks. Okay. For the actual perturbations on the weights, because that's what we do when every time we assemble the loss, we go to this method called flip out. I don't know if it's standard now, but anyway, so this is how flip out works. We carry out perturbations which involve a mean and a stochastic perturbation. We assume that perturbations on the weights are independent and identically distributed, that they're symmetric about a zero mean. The perturbation that we want to apply upon it is done as follows. We assume that all the training samples have a base perturbation, which we obtain by drawing from a normal distribution with the covariance of our surrogate distribution for the posterior, which I introduced in the previous slide, which goes into the KL divergence. So we draw it from there, and then we multiply it further by these random rank 1 sign matrices, right? So we take this perturbation from this distribution, but then, and the open circle here indicates an element by element multiplication. It's multiplied by this rank 1 matrix, where the vectors Rn and Sn are each just random vectors with plus minus 1s, right? For each sample. What this does is that because we're randomizing it, we get different perturbations over each sample, for each sample. And in a mini, and when you're doing mini batches here, what this does is it reduces the variance of stochastic gradients and flip out, right? So it helps with that. So when we're doing finally mini batch optimization, this is the form of our loss. It's pretty much what we had on the previous slide, except that now we know that when it comes to evaluating the weights in this term, we use flip out. Okay, so all of this, of course, is for the epistemic part of the uncertainty, because we're talking of uncertainty in the parameters, which just models what we don't quite know about the model, right? Which represents what we don't quite know about the model. Aleatoric uncertainty, we just add noise, right? So in the part that comes from the neural network, we get some representation and we add some noise denoted here by epsilon. We do this by adding some constant covariance here on the learned representation. Now, remember that there's another part that follows here. Once you've got this representation with some noise, that is passed through the residual. So it propagates through the residual. It gives you some noise in the residual as well. We then use the residual to actually evaluate the likelihood rather than using this field itself. And this is one of the reasons why we can kind of claim that we are doing something that's label free, right? So we define the likelihood from the residual. The idea being that, of course, if you've solved the problem, then your residual goes to 0. So we draw this, we compute the residual, right? But then we represent it through this normal distribution with a 0 mean and some covariance. Now, it's difficult to evaluate this covariance, especially if you have a nonlinear problem. It's difficult to evaluate it exactly. So what we do is that make that also a learnable parameter in our approach. So we put all of that together, and finally the batch-wise loss is represented as here, the KL term, the KL divergence term, and now we have a log likelihood. One more thing I should mention: when we construct this likelihood, we write it as a joint normal distribution for each component of the residual that we evaluate, right? So you will see that we end up evaluating the residual corresponding to each pixel. The little k here represents each pixel. So there's a joint distribution over all the pixels. And you can think about this as being equivalent to, in a finite element method, to looking at each component of your big residual vector, right? So imagine you're writing a joint normal distribution over all those components. That's what we're doing. And then we're requiring that each of those components goes to 0 by sort of, or we're trying to drive them to 0 by picking this 0 mean here. Okay. And then, of course, we have the log likelihood. So it becomes a sum over all those pixels. So capital K pix is the number of pixels in your image. Okay. All right, numerical aspects. I should introduce some terminology here. Now, remember, we're working with boundary value problems. Now, one boundary value problem is, of course, what everybody knows, but this is what we mean here by a single data point. So one data point for us is one boundary value problem that the PDE is using to learn. Okay. A data set then is a set of unique boundary value problems. We work with small and large data sets. Small data sets are 20 to 30 boundary value problems. A large data set goes to close to 200,000 boundary value problems. We need to do some augmentation. Oops, sorry. We need to do some augmentation. And epoch then, of course, as usual, is an iteration of the entire data set. We do training and validation and testing, so 80, 10, 10 splits. The testing data set has multiple boundary value problems that the neural networks have not been exposed to previously. We hand generate the testing data set for the small data sets. For the large data set, the testing is randomly generated. Okay, and randomly generated with random boundary values, random boundary conditions, and everything. Okay, so here is a critical part here. I'm just looking at my watch to see how I'm doing. Okay, how do we actually construct all of this? So you have this picture that I've shown you already a couple of times for how we think about the neural network architecture here. I talked about the channels that we're introducing, right? And I emphasize that really the channels are for the boundary conditions because that's what we want the system to learn. So now let's look at that. How do we do that? We come down to the second row of images here. I want to point out a few things to you. Observe that there's a square outside and then a colored domain inside. The big square outside is sort of the background. Within it, we paint some of it with the actual domain over which we're solving the problem. And here we want to rely upon the ability of CNNs to really recognize images. And we're seeking to make sure that CNNs recognize that you can have a big box, but the domain of interest is really something inside. How do we do that? We introduce some label. We use the label -1 to tell it where the big box does not contain a domain. So sort of the exterior domain is -1. The Dirichlet boundary condition, the Dirichlet boundary here is labeled with some number greater than 0. We fill the domain with -2s. Again, just some other label. You could pick something else. But what this tells us the network to do is to fill that with random numbers so that it doesn't learn anything ever from that, right? Because that just keeps changing. For non-zero Neumann boundary conditions, same deal, -1s in the exterior domain. The Neumann boundary conditions don't really come with any notion of a solution in there, so we can set the interior to 0, and we paint some number greater than 0 for where we have non-zero Neumann conditions. This would be if you had a nice domain which is aligned with the edges of the big box. When we have other domains where the edges are slanted, we have this sort of pixelated representation of the boundary. It leads to some issues with representing Neumann conditions. I'm not going to get into big details about it now because it takes some description, but if there are questions, I have backup slides to talk more about it. Okay, that's it. So that's what we're trying to do, trying to use the ability of CNNs to recognize images, right? And to see if they can also recognize the fact that this is a domain and this is not a domain, right? So that's why we're doing this labeling. Basically, for the large data set, it's the same idea. The difference is that for the large data set, because we're going to have so many of these boundary value problems, we need, when it comes to the Dirichlet channel, Dirichlet boundary condition channel, on the interior domain, we can afford to use zeros. In fact, we need to use zeros. Otherwise, the neural networks sort of get confused about whether the random numbers were supposed to be something about the boundary or boundary condition or not. You can get into more details about that if you're interested. But essentially, the idea is you label things differently. Label the interior and exterior domain differently. You need some labels to tell it what is a Dirichlet boundary, what is a Neumann boundary, and where it should not be paying any attention to any numbers, because we're never ever feeding it with any direct numerical solution from which we wanted to learn. So we never really feed it with anything inside the domain from which we wanted to learn. We're telling it to just be blind to the interior of the domain. Thereby, we're forcing it to try to figure out what the PDE is. Okay, all right. That is how we approach these input channels. I should mention this: all our implementations are with TensorFlow, added on to our labs code, which is called Mecanochem FEM. put together all of this is going to show up in a library that we call Mechanochem ML that will be released in the fall. Okay, and this is just the whole picture, right, put together. But what I haven't told you is how we actually go around using these input channels now construct the residual, and that's what I'm going to get into now. All right. Here's the idea. I talked about using images, really treating boundary value problems on domains as images, really making that connection because we're using CNNs and all that. So supposing you do have something like this, right? Supposing you have an image, it's a very coarse image, 25 pixels, 5 by 5 pixels here. It could be a 1D, over a 2D domain, but effectively a one-dimensionally driven diffusion problem, right? You may have some Dirichlet conditions here and you have some gradient, fine. The small squares are pixels. What we use here is the idea that you could pretty much put a finite element mesh on that, right? So every pixel is a node, gives you the idea of a finite element mesh, and that's what we use, right? In fact, that's exactly what we do. Now we say, okay, we have a mesh there, right, with nodal values from the pixels, right? So this is how we think about it. The key to then going ahead and developing anything like a finite element representation here is to just write out kernels which do all our standard finite element operations. For instance, if you have Dirichlet conditions here, you can write this kernel that we've denoted as I. It's a 5 by 5. You can write this kernel ID 5 by 5, map it then to a full 5 by 5 matrix over the entire 5 by 5 set of nodes. When it comes to the interior domain, when it comes to the bulk values, we do essentially the same thing. We write 4 other kernels denoted here as KB 1 through 4, and they're color coded here as green, blue, turquoise, and red. And what they do is pick the upper left, upper right, lower left, and lower right of each element, but then they operate jointly on the entire mesh rather than go element by element. We reshape them into a 5 by 5 by 4 matrix here. And then in order to assemble the residual, it turns out to be more convenient to vectorize them. So we just unroll that 2 of those dimensions of that 5 by 5 by 4 matrix here. It's convenient to do all your residual calculations on the entire mesh in this unrolled form. Reshape the residual back into this 5 by 5 by 4 form. The colors here just represent what you have from contributions from each element, the upper left, upper right, lower left, and so on, but computed for the entire mesh. Okay, put them all together just using shift operations, and then you can effectively assemble, do your standard finite element assembly operation by applying reduce sum, right? So without actually having to do loops. Essentially, it comes down to using kernels in a kind of sort of semi-smart but obvious way to get to what you want from what you know from finite elements. Okay. Same thing can be done for Neumann conditions also, right? So for Neumann boundary conditions, you just define these kernels, kind of obvious what you need to do when you think about it. And then you can add them on to your big global residual. Now you've added the blue here are the dark blue dots, open circles here represent the Neumann conditions, right? So you assemble all of this together. That's it. So now you have your residual defined at pixel-wise. And as I mentioned earlier, when I was talking about the loss for the elbow, right? The loss coming from elbow, I mentioned how we have a normal distribution that goes pixel-wise. Well, this is what we have, right? It's defined in terms of the residual. You have the residual value at each pixel. You can form this joint distribution, which goes into elbow. Okay. Couple of things to state here. Neumann boundary conditions tend to be a little problematic, and this is mainly because what is controlled there is not the solution itself, but the gradient of the solution. We're showing one such sort of failed calculation where when it comes to Neumann conditions, we have a network that is trying to learn a solution, learn a PDE over using as one data point, a problem for which this is the actual DNS solution. It is not given the DNS solution, it has to learn it from the boundary conditions. Anyway, it's trying to do that. It's going over many epochs here, 1900 epochs. You see, it starts out well, the sort of solution starts propagating, but it sort of saturates, right? It doesn't get to anything like this. This has to do with the fact that when we start out by initializing parameters, we the tendency, the tradition is to do a random initialization of the neural network parameters. This, by the way, is for a deterministic neural network. Anyway, so when you do randomization of the neural network parameters, it tends to be very far from a solution to the PDE. And so it just does not progress. The learning just does not progress. What we realized we had to do, one of the things that works here, is to use an approach that is common in finite element solvers, which is to start out with an initial guess of 0 for your solution. We did that after scaling and normalization, which is common for machine learning. That 0 gets mapped to 0.5 in our methods. So then when you start with what we now call 0 initialization of the parameters, learning does proceed, and we pick up the method picks up, learns the solution in 500 epochs. I should mention that the neural network that is learning the solution to this PDE is also learning the solution to many other PDEs. So in looping over these epochs, it's also learning over many other PDEs, and we're just showing you how it fails in learning a certain set of Neumann problems and does learn those if we do this thing of 0 initialization of the parameters. Okay, numerical examples. Let's see how this thing actually works. I'm going to start out by showing you a problem for steady state diffusion for 20 boundary value problems, the small data set. We used 5 different domains, and what I'm showing you here, the big square is this background grid, and the actual domain is the yellow region inside, right? So 5 different domains. Number 5 is the full background grid. Different boundary conditions, Dirichlet or non-zero Neumann boundary conditions. We did this for deterministic and probabilistic networks. So you can see some of the statistics, some of the information here, 33,000 to 66,000 parameters for the deterministic probabilistic networks, respectively. I talked about how we do data augmentation. This gets up to 1,024 for the deterministic network and 512 for the probabilistic network. It looks like we have to solve a number of epochs for the deterministic network, but I'll show you that we don't really need that much. The probabilistic networks need far fewer, and I'll explain why. I told you about the 0 initialization and so forth. Oh, I should also mention that the 0 initialization, sorry, just one thing. The 0 initialization that we do here, we need to do it only for the first 50 or 100 epochs, right? And then the solution procedure, it gets learned. All right, I'll mention other things as they arise. This is the details of the network. Let's go past that pretty quickly, but I'll be happy to go back to it if anybody wants me to. Okay, so results. Our first small data set of one network now learning 20 different boundary value problems for steady state diffusion. I showed you what the boundary value problems are that we gave it. Again, the green kind of patches outside here. The green L is where it's the exterior domain, right? This denotes the Dirichlet channel. So this is a Dirichlet problem. This is a Dirichlet-Neumann problem. Dirichlet conditions here, Neumann conditions on non-zero Neumann on the right, of course, 0 Neumann on up and down. It learned it. So you can see for the Dirichlet problem, that is the DNS solution. This would be the deterministic neural network solution, the mean of the Bayesian network, and the standard deviation. Across this dotted line, you see the solution, you see the DNS, the mean is in there, and you see the ±2 standard deviations. Of course, it pretty much comes very little variance at where we have the Dirichlet conditions. For the Dirichlet-Neumann problems, similar kind of results. We see more variance, of course, where we have the Neumann conditions, and that just shows that wherever we have gradient conditions, you basically don't do as well. Okay, and that was reflected in the difficulties we had with learning problems with Neumann conditions as well. But okay, I should point out that I'm showing you 2 boundary value problems here. This thing learned actually 20 different boundary value problems with, and I listed them on a previous slide. The loss for the deterministic problem, I mentioned that we went up to 20,000 epochs, but we really didn't need that. We could potentially have stopped at 5,000 and called it good enough, right? We don't really, not much improvement after that. That's for the deterministic neural network. All of these plots correspond to the Bayesian neural network. Now, the Bayesian neural network, how well it does is very much controlled by the amount of noise we add. we're considering three amounts of noise, 10 to the -4 to 10 to the -2 of the covariance of the noise we introduced on the neural network solution. I also mentioned that in the residual, that this loss propagates through the residual, and we try to learn the amount of noise that this introduces into the residual. It's sort of like a stochastic term. If you wanted to think about these as stochastic boundary value problems, stochastic PDEs, this would be like a stochastic forcing, right? That shows up in the PDE. And we are learning that amount. That is sigma 2. Sorry, it doesn't show up very well. What gets learned for that covariance is very much driven by the loss we introduce into the solution. When we have a noise of 10 to the -4 in the solution, what's it? We get to about 10 to the -3 in that noise in the covariance in the residual. And of course, as we introduce more noise, that also increases. The loss, we see declining here. It kind of gets it by about 200 epochs when there's very little amount of noise. When there's more noise, it takes a little more, right? It takes up to about 500 epochs to really converge. And out here, for one of those problems, I think this is for a Dirichlet and Neumann problem. As the noise increases, we see again the DNS, the mean, and you can see the variance. It kind of lies right over each other, but I think you're able to see here that as for the case with the biggest noise, we also get the most variance. Right, so this just shows how these methods perform. Essentially, oh, I realized there's one thing I forgot to mention. Okay, for all of these problems with Bayesian neural networks, we do this business of for the parameters of the Bayesian neural network, we initialize them with parameters obtained from a deterministic network that has not yet been fully trained for the same problem. So it's like the deterministic network starts getting some parameters. We take those and give them to the Bayesian neural network as the means of the weights. And this really sort of jumpstarts the Bayesian neural network. This is what we call warm start. I had it on a previous slide. I have it right here in this previous slide. I just forgot to mention it. But so we do this warm start of the parameters of the Bayesian neural network from the, I said sub-optimized. They can be, these are parameters obtained from a deterministic CNN with the same architecture, but not yet fully optimized. So we don't need to it's not like we need to get a full CNN solution before starting a BNN solution. We can start a CNN solution, take pre-optimized parameters, give it to the BNN to tell it that those are your means, now go, and it does pretty well. And that actually gives us convergence in a small number of epochs, relatively small number of epochs. Okay. All right. All right. Now we went to other domains, also steady state diffusion. This is a different network now learning a solution on an octagon. Dirichlet conditions in red and green, non-zero Neumann here, DNS, deterministic solution, mean of the BNN, and standard deviation here. This is with a 32 by 32 pixel size, number of pixels, 32 by 32. This is with more 64 by 64, solution improves. And we can also see back here, this is down here, I'm showing you the solution across a horizontal line with a 32 squared pixel mesh, 64 squared pixel mesh. And this is, I think, yeah, across a vertical line here, showing you the solution, the 32 square pixel mesh, 64 square pixel mesh. There's a slight improvement, unsurprisingly. This is like mesh refinement. Okay, this was a different network. But that was all. So all of that was for steady state diffusion. We now look to vector problems, linearized elasticity. Start out with an L-shaped domain. Dirichlet conditions here fixed. Let me see. Also, xn, both displacements are fixed on the bottom here. We're driving it with a vertical displacement on this side here. DNS solution, deterministic solution, mean of the BNN, standard deviation, and you see a plot of the solution along that vertical line. We see that the variance grows very quickly as you move away from this Dirichlet boundary condition, but Dirichlet boundary, it the mean kind of starts falling away from the DNS solution in this case. Across this horizontal line, again, we see that the variance grows, does a little better. So I should mention that for this problem, the solution doesn't do quite as well because the actual DNS solution itself is not very big, right? It's like a small, the numbers here are kind of small. So our method is trying to find solutions to numbers that are close to, that are not very big. And that's really seen here in our results, where we were trying to also extract what we get for the reaction on this bottom boundary. It turns out that the reaction in the x direction from the DNS solution is actually dead zero. The deterministic network is trying to get to zero. It's getting small values, but it's not quite getting there. The red are training values. The green are testing values or validation values testing values that are interpolated, right? They're between the training values. When we go to the BNN, we see there's quite a lot of variance, and so it looks like the BNN is getting solutions that are closer to zero, but that's because there's just so much variance, right? It's not doing very well here, honestly. Same here, same deal for the force in the y direction. It's close to zero, declining as the DNS shows. The deterministic network tries to get it. It does more poorly when it comes to the BNN because it gets very large variance here. I will mention that it gets larger variance relative to the solution simply because the solution itself is very close to zero. So it's having a hard time finding small solutions here. I will show you that when we go to nonlinear elasticity, where we can have much bigger displacements and bigger deformations, the methods do better. That's where we are. Another network now learning a different equation, nonlinear elasticity, 30 boundary value problems, 5 domains, 6 different sets of boundary conditions. Those are the actual 2D nonlinear elasticity problems being solved here, right? 2 different boundary value problems. As you can see, these are larger deformations. 2 boundary value problems, like I said, this is a Dirichlet problem, DNS, deterministic solution, mean of the BNN solution, standard deviation. This is for the displacement in the x direction. This is for the displacement in the y direction. I'm not going to get to details here, but we're also plotting the solution along this line and along that line, right? The x solution along this line, the y displacement along that line, and you can see how the mean does relative to the DNS and what the variance is. This is for a very similar problem, only it's Dirichlet Neumann, right? Dirichlet on the left, non-zero Neumann on the right. The Neumann conditions kind of worsen things a little bit. We kind of miss the DNS solution by a bit, kind of crack it, but you can see what we get. Okay, now let's go to this case in which I said that the large deformations actually help the solution when to do a little better. So this is a sort of reprise of that problem that I showed you on that L-shaped domain with linearized elasticity, where the network was doing poorly because the solutions, everything was pretty close to zero. So I'm not showing you the field here. What I'm showing you instead is the predicted solution, predicted reaction in the x direction when the red dots here show you the training, the green dots show you interpolated testing. By saying interpolated testing, testing values which are interpolations, meaning the driving fell between values that were used in training, right? So the driving displacement fell between values used in training. The black line is the DNS. We track it pretty well. The blue dots now are extrapolation values, right? So this is outside of the training, right? So how well does machine learning extrapolate solutions, right? This is always a bugbear for machine learning. We see we don't do so badly. This is for the x, for the reaction in the x direction. This is for the reaction in the y direction. We don't do so badly because if you look at these numbers, scaled relative to what we saw for the linearized elasticity problem, these are larger numbers, right? So we're really pushing the problem harder. The network actually does better when it has more to kind of bite into, right? Okay, now as we move rightward, we are decreasing the amount of training and increasing the amount of extrapolation testing. Okay, so the blue dots are extrapolation testing. And as you can see, I mean, unsurprisingly, it kind of tracks, but as we go to really small amounts of training and large amounts of extrapolation, of course, it really falls off the DNS solution. Not surprising at all. Okay, that was for the X displacements and Y displacement. But overall, it does better than the linearized elasticity problem simply because the numbers here are quite a bit larger. Okay, Yusuf, how am I doing on time?
I'd say another 5 minutes.
Okay,
yeah,
that's great. That's great. Yeah, basically we're into the final part. Okay, so all of this, by the way, every time I showed you a problem, whether it's for steady state diffusion on a square domain, on the octagon, or linearized elasticity or nonlinear elasticity, was a different PDE. And in each case, it was a different network, right? In particular, for all of those steady state elasticity problems, steady state diffusion problems that I showed you, which were all of these ones, right? There's one network learning 20 boundary value problems on a square domain, another network learning steady state diffusion on an octagon. Now we come to this question of asking how well does it do across domains and even unseen domains. The images that you see flashing in front of you, the GIF that you see flashing in front of you is constructed from 500 boundary value problems across different polygons, quads, pentagons, and hexagons that we used in learning, right? And these are three different channels, Dirichlet on the left, the two non-zero Neumann on the right. Also generated randomly are boundary conditions, boundaries itself, the values of boundary conditions, how they vary, and all of that. So the data set consisted of almost over 183,000 problems. You can see the number of quads, pentagons, and hexagon boundary value problems. 500 unique shapes, for each unique shape. Boundary condition locations were randomly selected. The boundary condition types also randomly chosen, but these were constant, linear, quadratic, sinusoidal. The values were also randomly generated. The testing set was a smaller set of 320 boundary value problems also generated randomly. The network and so forth. Okay, this is what we see for the loss for the deterministic solution. Again, we drove it all the way up to 35,000 epochs, but basically we could have called it quits at 5,000 epochs. Because now, okay, I'm going to show you the results from a single neural network trying to learn all these solutions, right? Or learn a PDE solution to all these different boundary value problems. Unsurprisingly, it has a few more parameters. We had more like 33,000 for the networks we saw earlier. We go over 100,000 parameters now. Okay. All right, so single network learning all these problems, and these are testing, randomly generated, so I don't really know exactly what's going on here. We have Dirichlet conditions, varying Dirichlet conditions, DNS solution, predictive mean from the BNN and the pointwise error. Doing not so badly. Another Dirichlet boundary value problem, DNS, predicted mean, Dirichlet Neumann problem. The different colors on these boundaries simply mean that the conditions are the boundary condition values are also fluctuate or varying, right? And randomly picked. DNS predicted mean doesn't do so badly. This problem, also Dirichlet Neumann problem, did somewhat more poorly, but if you look at the actual values, you see that the variation here is much less than in some of these other problems. So it's having, again, difficulty where there isn't that much variation in the solution, right? There isn't that much for it to bite into. Quads, same deal with pentagons. Single neural network, learn quads, learn pentagons. You can very quickly look at the solutions, how they do. They do okay for the Dirichlet, for some of the Neumann, they do poorly. But again, if you look at the numbers here, see there isn't that much change relative to some of the other cases in which it does better, right? So that's where it has trouble. Hexagons also, same deal. Single network learning all of these solutions and being tested on these. Finally, we gave it a domain it had not seen before. The network does not know at this point that heptagons exist as a mathematical domain, as an object. Doesn't do so badly, okay? You look at, well, this one didn't do so well, but this here, in this case, it did okay, and so on, right? Again, if you look at the numbers, you see, yeah, but there isn't that much fluctuation. It seems not to do that well. Again, we use a mixture of Dirichlet and Neumann conditions. Okay. To summarize what we see here, we've summarized our errors here. organized by each type of domain, each shape of domain, 80 boundary value problems in each case. The Neumann conditions, the L2 error is a little, when we have Neumann boundary conditions, the L2 error is a little bigger. All of this should be compared with a max norm of the solution of 1. Right? So that tells you about what the error is. Dirichlet conditions do better. I should mention that in each case, the error that we're reporting is also averaged over all boundary value problems for that type of domain. Getting back to why we wanted to do this as for high throughput solutions, how does this compare even with the very small, admittedly very small finite element problems that would be taken to solve these problems, right? So 16 by 16 to 64 by 64 meshes, right? FEM solutions using our code, you can see how much time it takes. With the BNNs or with the deterministic neural networks, we beat it by almost 3 orders of magnitude. I'll also mention that these are very small problems, so we're not yet into the solver-dominated regime at all, right? We're very much assembly-dominated for finite elements. The neural network actually does better relative to the finite elements. If you really look at these numbers, that this ratio is about 200 out here, improves to almost 800 back here. And this is when the finite elements are still in their assembly-dominated regime. If you're using a direct solver, as we're doing here, to move into the solver-dominated regime, the finite elements would start scaling as the cube of the size of the mesh and would do even more poorly. Of course, we don't really know how the neural networks would do there. We hope they do better. Okay, I can get into great details about what we see with all these solutions and how things vary and all that, but we've summarized them in just these in these 2 bullet points here. The results are not surprising. We need to have more uniform distribution of boundary locations and extremes of boundary values used in training, right? So you really need to spread out the training over the kind of accepted regime for this problem, however you define that regime after normalization and so on. Predictions are also more accurate if the extremes when you're testing are not near the extremes of your training data sets, right? Of course, right? And what you would expect, right? Ultimately, these methods still don't do great when it comes closer to extrapolation. My summary slide here, I'll just mention the known, all of this, a subset of the work I presented here appeared, is available on arXiv, not the latest results across different domains. Known challenges, Neumann conditions are a problem. We use up to 1 billion data points where now you start counting the pixels also, right? So we can get to really large data at some point as we go to learning more and more conditions and more domains and all of that. That's known. The slanted edges are a bit of a problem here because they have a pixelated representation. We believe we know something that we can do here. We're working on it. We need to have this warm start for BNN parameters. What works here, I'll summarize these 5 bullet points. Essentially, one can get networks that learn boundary value problems on varying domains, locations, and values, can make predictions with interpolation and extrapolation with limited success, but some success. It can make predictions across new domains and new boundary conditions. And yes, we can do UQ, of course. We're extending it currently to other PDE systems, of course. What would be really nice is if we can get a good way to do parameterized domains even from this pixelated representation. Acknowledgements to the funding sources, and this is Shashwan, who of course has done all of the work behind this. So great, thanks very much. Hopefully I'm not hugely over time.
Thank you very much, Krishna. Yeah, no, I think we have about 2 minutes left for a couple of questions, and I encourage people just to unmute and speak up.
This is Zhou Lu. Can you hear me?
Mm-hmm.
This is Zhou Lu from Lam Research. I actually have a question about the technical detail of how you constrain the posterior. So I assume when you use the KL divergence to constrain your posterior, you assume the posterior distribution is a multi-dimensional Gaussian. So what I want to learn about the detail about is whether you only constrain the diagonal terms of the variance matrix, ignoring the variances, the covariances.
No.
Or you constrain the entire covariance matrix.
The entire covariance. Yes, we're not doing just the diagonal terms. Yeah.
Thank you.
Yep.
if time allows, I have another question. Have you thought about using Bayesian approach to do model selection? Because if you make your neural net with very large capacity, you may have a too large variance. You may not want to, right? So by looking at the predictive distribution, whether you can say something about your model capacity.
So we have used it for models. We've used it for a limited problem, not for any of these PDEs in the context of model selection. We've actually played around with some of the COVID data, which is, of course, freely available and all that. So we've tried to do more. We've done model selection with this approach with the BNNs in order to do model selection for the so-called third epidemiological models, susceptible, infected, recovered and deceased populations, which is it turns out to be a smaller problem than these, because those are not PDEs, those are ODEs, so there are far fewer parameters that we need to use. So what was the second part of your question? You had a question related to the size of the network on that?
Right, yeah, because by looking at the predictive distribution, you know the variance and the biases of your model. So whether you can use this result to do model selection, because sometimes you don't know how large the neural net you want to start with. Sometimes you want to train.
Oh, I see. You're asking about model selection for the size of the network instead, by using variance. We have not done that, I would say. No, we have not tried to use variance in that direction, but yes, it's available.
Great, thank you for the great talk.
Thank you.
Thank you. So we're over the hour, so I should let anyone go who needs to go. But I think Raul had a question, or at least I see.
I'm going to talk to Krishna in a half hour.
Hi, Raul.
Okay. Okay. Very good. So with that, I think we should end the formal session, and let's thank Krishna again for a really interesting talk.
Thanks very much.
Virtual claps.
Thank you.
And, yes. We'll see everyone the next round of seminars in the fall.